All right, welcome back. Today we're going to talk about deleted files and recovering deleted files. I'll go through a simple example, and the homework will also have you do that on your own with some guided information. And the lab will actually be a little bit more in depth, and you'll have to go through and recover a bunch of files and then identify information about those particular files that were recovered. So, when a file is deleted, it actually still exists on the drive. What happens to the file differs by the file system, but the data itself still exists inside of the sectors. So when you delete a file, the operating system will mark the space as free, and that differs by file systems, but it doesn't zero the data. So during that time after a file is deleted, before those sectors are overwritten, the data is potentially recoverable. So the operating system will update the allocation table, so the file allocation table inside of like the FAT12, 16, or 32 file systems, the MFT for NTFS, the inode table for Linux type systems. It'll mark it as free. Those sectors that had that file will now go back into the free block pool, and the next time a file is written, it can use those sectors and start overwriting it. So until that happens, you have a recovery window. This is why if a file is deleted, the first thing that you have to ensure is that no changes are made to that drive, because any changes has a potential to overwrite existing deleted data. So this is why write blockers exist. This is why if on your own system you happen to delete a file, the first thing you do is you immediately shut down the system and you pull the hard drive, and you don't touch it with a live system until you're sure that no changes can be made to the actual drive any further. So talking about FAT, and this says FAT32, but it's the same between FAT12, FAT16, and FAT32. So before a file is deleted, you'll have your directory entry and the file name inside of that. So key thing to note with FAT is the files are stored with the directories, and the directories are stored with the parent directories, and the parent directories are stored with the volume. There isn't a single location at the beginning of the drive which lists the location of all the files. It's really a linked list sort of storage, to where you go to the directory and then you can iterate through where the files are inside of that directory. The starting cluster or the starting value will be the first letter of that particular file. It has the file size, it has chain and everything else. And the chain is how the drive knows where the actual data is compared to where it is in the sectors. When a file is deleted, all that happens is the first character of the file name is changed to the byte hex E5. Everything else stays the same. Nothing else changes. The other thing is the cluster chain is released, so then it can actually start to overwrite those, and they're marked as free. But because really the only thing that happens is the first character of the file in that directory is changed, everything else still stays. That means that when you go to recover the information, you can get the original file name, you can get a lot of information, and you'll know where the file originally existed on that particular file system. Now, contrasting this to NTFS. So NTFS inside of the MFT, when a file is deleted, it's marked as not in use, but not zeroed, which means that all the metadata will persist, including file name, timestamps, size, data locations, all of that. It's just marked as not in use. The NTFS change journal will record a delete record for that file with that particular timestamp, and it will retain that for quite some time. It will use the data runs to describe where the file content is stored. So this is different different compared to the cluster idea that FAT32 strictly uses. It uses what's known as a virtual cluster number and a logical cluster number. So kind of the difference between there is a file has a virtual cluster number, which is its relative offset from the beginning of the file. So to seek to twice the size of a cluster followed by a read will return the data at the beginning of the third VCN. There's also a logical cluster number, which describes the offset of the cluster from some arbitrary point in the volume. So that's going to be equivalent to kind of a relative mapping. So there's a mapping from your virtual cluster number to your logical cluster number in the entry, so it knows where the file exists and how to access it. And then finally, there's what's known as alternate data streams. And we'll talk a little bit more about these in a couple of subsequent videos, and we'll see these. But files in NTFS can have what's known as an alternate data stream. And it's very useful. It's also been used for malware and malicious purposes, but alternate data streams are not deleted the same way. So the zone identifier, for instance, that is an alternate data stream which identifies where a file came from. So when you download a file from the internet, it will automatically add on a zone identifier to indicate that, hey, this came from a network location, and this is the URL that it was retrieved from. And that will persist and survive deletion the same manner as the primary stream. So from a forensic standpoint, that zone identifier and other alternate data streams are very, very useful to have, because that will allow you to provide more information as to where that file was from and everything else. ext4, and again, where there's other file systems out there, we're just touching on some of the big ones. This has the inodes, and it will mark the inode as free in its inode bitmap. Basically, it's kind of database. It becomes available for use. However, that inode may contain some of the residual metadata. The directory entry will also then be removed, and the file name is removed from the parent's directory entry list. Unlike FAT32, it completely removes directory entry as opposed to just changing the first character of the name. So actually recovering file names on a ext4 system is quite a bit harder and may not be possible depending upon how the deletion has happened. It will then clear the block pointers and are zeroed, unlike older versions of ext, which makes just going through the inodes and recovering files that way quite harder. The data blocks are still there, but the inodes are zeroed out. And so this is why you end up using a lot more file carving and journal analysis and not relying directly off of inodes. What we'll do in this class is using an ext, or not an ext, a FAT file system to recover files from, because it's easier and it gives you an idea for that. And if you wanted to have a challenge, then you can find ext and NTFS file systems online pretty easily to run recovery tools on there to see how you would actually go about recovering the same files that you would recover from a FAT12, 16, or 32 file system. And again, ext4, they have a journal, and that journal records file system operations, including deletions. And so as long as that journal has not been flushed and still maintains that entry, you can go through the journal and find the file names, inodes, timestamps, all sorts of other information, which is, again, why it's important that when a file is deleted, the drive is removed right away, and then analysis is run before any changes are made to that drive. So, talking about the recovery techniques, FAT32 uses that hex E5 marker. NTFS, the MFT, has a flag for deletion. ext4 completely removes the entry. Inode, FAT32 doesn't use an inode. The recovery tools still list an inode. It's just the number that they assign to it. NTFS retains the inode, and ext4 zeroes it out, so you can't really do inode recovery. File carving, pretty easy. Well, when I say easy, it's pretty reliable on FAT32 and NTFS, and that's what you use on ext4. We'll go through file carving quite a bit more, and we'll actually see examples of it, but that's a way to recover files when you don't have the beginning part of the file to know where everything is stored. Journals, FAT32, there is no journal. NTFS and ext4 both have a journal, so you can use a lot of the journal information for recovery. Tools, Autopsy is one of those that is used for all of those. Foremost and Scalpel is used for carving. We won't use Autopsy, but we will use a lot of tools from the Sleuth Kit, and we'll go through those because it's command line and quite effective for recovering files that way. There's also FLS, which is the tool that we will be using that will work pretty well on FAT32. I haven't gone through NTFS too much for that, but it should work on that. And ext4, it will kind of work, but again, file carving is what you would generally do. So key takeaways: deleting a file doesn't erase the data, only removes the reference to it. ext4 removes more of the references. FAT32 removes just a single character of the reference, but the data still persists. FAT32 sets the hex E5. NTFS marks the MFT entry as not in use. ext4 zeroes the block pointers, but leaves all the data there. And depending upon how quickly you can get access to that drive and start your analysis, depends upon how likely you are to recover those particular files.